Good morning, everyone, and thank you for attending this awesome conference. I get very excited about elliptic curves, especially computations involving elliptic curves. I did not send Alvaro this, but I could send him a rank 12 elliptic curve that I found um, with the hope of getting a special t-shirt also, but that competition really was for the participants of the summer school. Anyway, so I want to talk today about three-adic images of Galois for elliptic curves over Q. So this work is joint with Andrew Sutherland and David Zurich Brown. I know that I've seen Andrew Sutherland around here at the conference. So to start out with, I'll first say that the talks earlier in the conference, especially the talks yesterday afternoon, have defined a lot of the notation that I will want to use. And I'm going to take full advantage of that. So if E over Q is an elliptic curve, I'm going to let En be the set of n torsion points on E. And so if K over Q is a Galois extension and the n torsion points on E are contained in the K points of E, then for every sigma in the Galois group of K over Q, when you restrict sigma to the n torsion points of E, this gives you an automorphism of En. En as an abelian group is isomorphic to Z mod NZ squared, and since the automorphism group of En is isomorphic to GL2 Z mod NZ, this gives you a map, the mod n Galois representation from the Galois group of Q bar over Q to GL2 Z mod NZ, given by taking an automorphism and just restricting it to the action of En. So these Galois representations are very important objects in modern number theory, and they play a number of important roles. So they are relevant for proving the modularity of elliptic curves. So Andrew Wiles did a significant chunk of that for elliptic curves over Q. And people have worked a lot on proving modularity of elliptic curves over more general sorts of fields. Another thing which is connected with this is the modular method for solving Diophantine equations. So the solution of Fermat's last theorem is probably the most famous example, but two other important examples are the solution of the equation x squared plus y cubed equals z to the seventh by Poonen, Schaefer, and Stoll, at least when x, y, and z are relatively prime in 2007. And also the problem of finding all perfect powers in the Fibonacci sequence. The only perfect powers that are Fibonacci numbers are 0, 1, 8, and 144. That was also done using the modular method in part. And another application in sort of a different direction is the inverse Galois problem for PSL2 of FP. So there was a lot of early work realizing PSL2 of FP as a Galois group for various specific primes P using elliptic curves. And then the problem was eventually finished off by David Zaguina also using Galois representations attached to elliptic curves. So let me talk some about the properties of these Galois representations. So the determinant map from Gal Q bar over Q to Z mod NZ star is surjective. In fact, if you look at the fixed field of the determinant inside the n torsion field of the elliptic curve, that field is Q adjoins zeta n. Another thing is that there's a matrix M in the image of rho En that's conjugate to either 1, 0, 0, negative 1 or 1, 1, 0, negative 1. This is a result of David Zaguina, and this is just because complex conjugation exists. Complex conjugation is an element of Gal Q bar over Q, and we can figure out how it has to act on the n torsion of an elliptic curve. Mazur's program B is given a number field K and a subgroup of GL2 Z mod NZ to classify all the elliptic curves E over K for which the image of rho En is contained in H. So this is a problem that a lot of people have been interested in for a while now. So I want to talk about what's known in the case of prime modulus. So if P is a prime number and this representation rho EP is not surjective, then the image of rho EP is contained in a maximal subgroup of GL2 of FP. So the possibilities are, options for the images of rho EP are Borel subgroups, those that are upper triangular mod P. They're normalizers of Cartan subgroups. So a Cartan subgroup is a subgroup isomorphic to FP star cross FP star. That's a split Cartan subgroup. Or a subgroup isomorphic to FP squared star, a non-split Cartan. And their normalizers are maximal subgroups of GL2 of FP. And the final option is exceptional subgroups, groups whose image in GL2FP mod scalars is isomorphic to A4, S4, or A5. Now, I will say that these are not all the maximal subgroups of GL2FP, but these are all the maximal subgroups where the determinant is surjective. So what do we know about the possibilities for rho EP to have one of these images? So in 1972, in his Propriétés Galoisiennes paper, Serre proved that if p greater than or equal to 17 is prime, the image of rho EP cannot be contained in an exceptional subgroup. This is not true for p equals 13. There are elliptic curves over Q with exceptional image, mod 13 image for p equals 13. Mazur proved in 1978 that if you have a non-CM elliptic curve over Q, the largest prime p for which the image of rho EP lands in a Borel subgroup is 37. And then Bilou, Parent, and Robledo in 2 papers show that if p is greater than or equal to 17 and E is non-CM, the image cannot be contained in the normalizer of a split Cartan subgroup. So one thing which is conspicuously missing from this slide is any mention of what happens for the normalizer of a non-split Cartan. And that's a case that mathematicians don't yet know how to handle. So we believe that if E over Q is a non-CM elliptic curve and p greater than 37 is prime, then rho EP is surjective. But we don't really know how to prove that because we don't know how to handle the points on the, handle the possibility of the image being a non-split Cartan. Okay. So we're going to look at a slightly different question. We're going to fix a prime p in elliptic curve E, and then for each n greater than or equal to 1, we have a mod p to the n Galois representation from gal q bar over q to GL2z mod p to the nz. These are compatible. If you take the mod p to the n representation and reduce it mod p to the m, you get the mod p to the m representation. So you can package these in a single p-adic Galois representation. So here Zp is the ring of p-adic integers. This is the inverse limit of z mod p to the nz. So we're interested in fixing a small prime p and determining all the possibilities for the image of rho EP for elliptic curves over Q. So I worked on this with David Zorc-Brown, and in 2015 we wrote a paper classifying the image of the 2-adic Galois representation for non-CM elliptic curves over Q. And there are a disturbingly large number of possibilities. There are 1,208 possibilities for the image of rho up to conjugacy. The index can be at most 96, and the image of the 2-adic Galois representation always contains all matrices congruent to the identity mod 32. It's a theorem of Serre that the image of rho EP to the infinity has to be a finite index subgroup of GL2ZP. And the theory of modular curves, which I'll introduce soon, will allow you to see that there are only finitely many images that you will get as you vary over all elliptic curves over Q. So this is for the non-CM case. I want to mention that Alvaro Lozano-Robledo has handled the CM case for all primes P, and also not just for elliptic curves over Q, but elliptic curves over Q adjoin the J invariant. So the goal of the present talk is to talk about what happens for P equals 3. So I worked on this with Drew Sutherland and with David Zorc-Brown, and we can prove that if E over Q is a non-CM elliptic curve, then the image of rho E3 to the infinity is one of 47 subgroups of GL2Z3 of level at most 27 and index at most 72. And every single one of those images occurs for infinitely many elliptic curves over Q. Or the image of rho E3 to the infinity is contained in the normalizer of the non-split Cartan mod 27. We don't think that that second case occurs. We don't think there are any elliptic curves over Q that are non-CM where the 3-adic image is contained in the non-split Cartan mod 27, but we don't know. The index of the image in GL2Z3 is either 1, 2, 3, 4, 6, 8, 9, 12, 18, 24, 27, 36, 72, or it's a multiple of 243. And the multiple of 243 corresponds precisely to the image being contained in the non-split Cartan mod 27. Okay. So I want to mention some applications of this theoretic classification. So despite the fact that we do not yet have a preprint, there are a number of projects that are finished or that are underway that rely on results like this. So torsion growth of elliptic curves over Q for degree less than or equal to 23. This is a preprint by Gonzalez Jimenez and Philip Nyman. There's work that I'm working on with Abby Rodon, David Gill, and Laurie Watson, where we classify the non-CM isolated points of odd degree with rational J invariant on x1 of n. This is related to Bianca Vray's talk from Friday. We can say something about the CM points as well, but we have a complete classification of the non-CM points. And there's a project I'm working on with Michael Serre, David Lombardo, and Sebastian Toronto about L-adic Kummer theory for elliptic curves over Q that also we're hoping to use these results in a productive way. All right. So I want to start talking about modular curves. So this is the subject of several previous talks. If I have an elliptic curve over Q, I'm going to use this formula for the J invariant. This is an important invariant. If two elliptic curves are isomorphic, then their J invariants are equal. Conversely, if I have two elliptic curves defined over a field K and their J invariants are equal, then E and E prime are isomorphic over some extension of K. But in general, they don't have to be isomorphic over K. So I'm going to fix a subgroup H of GL2Z mod NZ that contains minus the identity. The situation is a little bit more complicated for subgroups that don't contain minus the identity. But associated to this subgroup H, there's a modular curve Y sub H. And I want to say a little bit more about this. So if K is a number field, the elements of Y sub H of K are in bijection with pairs, elliptic curves, and H orbits of isomorphisms between En and Z mod NZ squared. So let me fix this. I hope you can see that annotation. I took it away. Whatever. Okay.
It was visible.
Okay. So the curve Y sub H is not projective, but we can make a projective curve by adding finitely many cusps to the curve Y sub H. So cusps correspond to certain sorts of cubic curves that are singular. So the curve X sub H is geometrically connected if the determinant map from H to Z mod NZ star is surjective. The other thing, and this was mentioned in Rockvi's talk yesterday, that if you have an elliptic curve over a number field K, and the J invariant is not 0 or 1728, then there is a K point on this curve X sub H associated to E if and only if the image of the mod N Gao representation is conjugate in GL2Z mod NZ to a subgroup of H. Rockvi had H transpose in her theorem yesterday, but whether or not that's true depends exactly on how you define what equivalence classes you put on these isomorphisms between En and Z mod NZ squared. So if you have two subgroups of GL2Z mod NZ, there's a natural morphism from XH1 to XH2. And we'll often use the map that goes from a subgroup H to the whole group. And that map is, so the whole group is modular curve is P1, and that map will take an elliptic curve to its J invariant. All right, so I wanted to give a few examples of modular curves and how they parameterize elliptic curves. And I wanted to use the modular curves x0 of n. These parameterize elliptic curves with a cyclic n isogeny. So if n equals 2, having a cyclic 2 isogeny is the same as having a rational point of order 2. So in this situation, x0 of 2 is isomorphic to P1, and here's one such isomorphism that sends a point T to the J invariant T cubed over T plus 16. This might look slightly different than models for x0 of 2 that you have discovered in the past. This is the one that comes out of my work with David Zurich Brown on the p-adic classification.
Hey, Jeremy, there's a question.
Yes.
Rockvi asks, that depends on the action. left
Yes.
or right?
That's correct. Whether the image is H or the image is H transpose, and this depends on whether you identify elements of En with column vectors in Z mod NZ or row vectors in Z mod NZ. And for better or for worse, different people have used different conventions in their work. So I think David Zegwina often uses column vectors, where Shimura and DZB and I in our p-adic work use row vectors. Okay, so for this modular curve, there are two cusps on x0 of 2. Those correspond to t equals infinity and t equals minus 16. So in other situations, if you have an elliptic curve over Q whose J invariant is not 0 or 1728, this has a rational point of order 2 if and only if the J invariant of V has the form t cubed over t plus 16 for some rational number t. And that's the sense in which the modular curve x0 of 2 parameterizes elliptic curves with a rational point of order 2. Let's look at some more interesting examples. So x0 of 11 is this modular curve, y squared plus y equals x cubed minus x squared minus 10x minus 20. So this elliptic curve has precisely 5 rational points on it. 2 of those 5 rational points are cusps, the point at infinity and the point where x is 16 and y is 60. Those are cusps. There are 3 other points, precisely 3 other points on this elliptic curve. Here are what the points are, and then they map to these 3 J invariants, minus 32, 768, minus 2472, 9001, and J equals negative 121. What that means then is that there are precisely 3 J invariants of elliptic curves over Q that have a cyclic 11 isogeny. So here are 2 more examples. So x0 of 27 is isomorphic to the Fermat cubic. This curve does not have very many rational points on it. It has 2 cusps, and it also has a rational point that corresponds to an elliptic curve with Cm by the order with discriminant minus 27. The Fermat quartic is isomorphic to x0 of 64. The reason for this dates back to a theta function identity of Jacobi. So it was proven in 1934 that there's only one non-trivial quadratic point on x0 of 64, and here it is, 1 plus root negative 7, 1 minus root negative 7, and 2. And because x0 of 64 parameterizes elliptic curves with 64 isogenies, that means that there has to be an elliptic curve over Q adjoin square root of negative 7 with a 64 isogeny. In fact, this curve is a CM elliptic curve, a curve with Cm by 1 plus square root of negative 7 over 2. This ring contains an element that has norm 2, and that means the elliptic curve has an endomorphism of degree 2. And if you just compose that endomorphism with itself again and again and again, that gives you cyclic isogenies of any 2-power degree that you like. And that's the reason that you get a cyclic 64 isogeny for this elliptic curve. Okay. So Faltings' theorem says that if you have a curve over Q with genus greater than or equal to 2, there are only finitely many rational points on the curve. It also is true that as the index of h in GL2Z3 goes to infinity, the genus of the modular curve x sub h also goes to infinity. So as a consequence, if the index of h is high enough, then x sub h of q will be finite. So we start by enumerating subgroups h of GL2Z3. Once we've enumerated all the subgroups we need to, we compute models for all of these modular curves x sub h. And we try to provably find all the rational points on these curves x sub h. And so this is what I'm going to talk about for the remainder of my talk. So in finding subgroups, we're going to start by looking at some specific ones. So we want subgroups where the determinant map is surjective. That will mean the corresponding modular curve is defined over Q. We want H to contain an element conjugate to 1, 0, 0, negative 1. that will be necessary and sufficient for the modular curve xh to have real points. I mentioned at the beginning that we either need 1, 0, 0, minus 1 or 1, 1, 0, minus 1. Those two matrices are actually conjugate in GL2Z mod NZ if n is odd. We want H to contain minus the identity. And we also want it to be the case that there's no larger subgroup where the modular curve has genus greater than or equal to 2. This last condition is what reduces the set of subgroups we have to look at to a finite set. And the reason we can impose it is that if we have a modular curve x sub k of genus greater than or equal to 2, it only has finitely many rational points. If we can find all of those finitely many rational points, any rational point on the modular curve xh has to map to a rational point on xk. And so we can just find the rational points on xk and understand the theoretic images for elliptic curves on those modular curves. Okay, so there are 80 conjugacy classes of such subgroups in GL2Z3, and the index of those subgroups can be as large as 729. Okay. So now we're going to start computing equations for modular curves. I could talk more about how I compute the equations, but this is something that's a bit computational and a bit technical, so I think I won't give a lot of detail about it. So we start with x0 of 1. The J invariant map from x0 of 1 to P1 is an isomorphism. And what we do in most cases, but not all cases, is when we have a subgroup H in our list, we look for the subgroup H tilde that's also in our list where the index is minimal. And then what we do is we construct xh as a cover of xh tilde. To do this, we work at the level of function fields. The function field of the modular curve x of n, which is the smallest modular curve of level n you can find, is a Galois extension with Galois group GL2Z mod NZ mod plus or minus I. This was mentioned by Rockvi yesterday. And we are looking for modular functions. This function field can be identified with modular functions of level n, functions from the upper half plane to C that are holomorphic and that satisfy f of az plus b over cz plus d is equal to f of z for every matrix A, B, C, D in gamma of n. Here, gamma of n is all matrices congruent to the identity mod n that are in SL2Z. We also insist that the Fourier coefficients of the function f live in Q adjoins zeta n. So that's the function field of this curve x of n. And we want to find the subfield of this that's fixed by H, where H is our subgroup of GL2Z mod NZ. So we want to construct elements of this function field that are fixed by H. And for that, we need some good building blocks of functions in this function field. And what we do is we take a row vector in Z mod NZ squared, where the GCD of C, D, and N is 1, and then we build this function G sub A of Z, 9 over pi squared times this Weierstrass P function. The lattice associated with this Weierstrass P function is generated by 1 and Z. This is a weight 2 modular form for gamma of n. A weight 2 modular form is not exactly the same as a modular function, but we look at ratios of weight 2 modular forms, and those give us modular functions. Also, it's very easy to see how GL2Z mod NZ acts on these functions G sub A. So we take linear combinations and products of these G sub A's to obtain a modular form for the subgroup H that's invariant under H. We keep track of the images of this function f as m ranges over cosets of H in GL2Z3. And using that, we can construct the minimal polynomial for our modular function H over Q adjoin H tilde and get a model of the modular curve x of H. So if I had infinite time, I might give you an example at this point, but I think I'll talk a little bit about what we do in some other cases. So in higher genus cases, where the degree of these coverings is quite large, we'll use a variety of modular forms tricks just to construct Fourier expansions of weight 2 cus forms in gamma of n Q adjoins zeta n that are fixed by the action of H. We do this with some tricks. There's some more systematic ways to do this. In particular, there's some papers on arXiv by Aranisov and David Zywina that compute these spaces using modular symbols. The benefit of knowing modular forms in these spaces is that they correspond to holomorphic differentials on the modular curve x sub h. And if you know a basis for the space of holomorphic differentials, you can use these to compute the canonical model of x sub h, which is a nice model to work with. So that's all I'll say for the time being about computing models of modular curves. I want to go on and talk about how we find the rational points. One more slide about what we find. So if we find that a curve x sub h tilde that has genus 1 and only has finite many rational points, we don't need to consider any subgroups h that are proper subgroups of h tilde. So when we're done computing models of curves, what we find is we get 22 genus 0 curves isomorphic to P1. We get 5 genus 1 curves, and every single one of these genus 1 curves has finitely many points. We get 4 genus 2 curves, 3 genus 3 curves, 4 genus 4 curves, a genus 6 curve, a genus 12 curve, and a genus 43 curve. When we were doing the 2-adic classification, we never had any curves that had genus greater than or equal to 7. And so the genus 12 and the genus 43 are maybe more concerning or more difficult than what happened in the 2-adic case. And I'll talk about each of the 3 very high genus curves. So now we're in the situation where we want to provably find all the rational points on these modular curves. This is a challenge. Faltings' theorem is not effective. And it's not clear yet that we have an effective way to provably find the rational points on any curve. The main technique that we'll use is étale descent. So let me tell you briefly about that. So if you have a curve C of genus G, we want to search for an étale triple cover phi from X to C.
Hey, Jeremy, before you get too far into this slide, there is a question. The question is, are there any conjectures for the other p-adic cases?
Are there conjectures? There certainly has been a decent amount of work done on some of the other cases, and I feel like we're about as close to understanding the situation with p equals 3 as we are to understanding the situation with p equals 5. But I think we know a little bit less about p equals 7 and p equals 11. I do believe the p equals 13 case is essentially done, that we know the 13-adic image of Galois for every elliptic curve over Q. And the cursed curve was a big part of understanding that. Okay, so we're looking for étale triple covers of this curve, modular curve C. Saying that a morphism of curves is étale is essentially the same as saying that the morphism is unramified. And we want these extensions also to be Galois. And so we're really looking for Z mod 3Z unramified extensions of C. And this Z mod 3Z unramified extensions of something correspond to elements of order 3 in the Picard group. And so what we're really doing is we're looking for 3 torsion points in the Jacobian C. So the beauty of étale descent is that this covering will have finitely many twists, and it will have the property that every rational point on C comes from a rational point on one of the curves x sub d. You might say, help. We're replacing the problem of finding the rational points on one curve with finding the rational points on a whole bunch of curves that all have higher genus. The answer is, and I don't understand exactly why this is the case, but it seems that the Jacobians of x sub d seem to be sort of more reducible than the Jacobian of C, and so we can find maps from x sub d to lower genus curves. So here is an example. So the genus 6 modular curve that we work with is a Picard curve. It's a Z mod 3Z extension of P1, and here's a nice model for it. Y cubed equals this degree 4 rational function. So we're interested in étale covers of this, and we can write down in a family of étale covers. So we let d be an integer that's either 1, 3, or 9, and we let x sub d be this curve. dy1 cubed equals this quartic, and dy2 cubed equals this cubic. So each of these, so these curves are really living in P3. They have genus 16. But if you just forget about y2 and look at the first equation, that's a genus 3 curve. If you just forget about y1 and look at the second equation, that's a genus 1 curve. So if d is equal to 3, the second equation has no theoretic points. And so we know that there are no rational points on that curve. If d is equal to 9, the first equation defines a genus 3 curve whose Jacobian has rank 0. Magma has the capability of computing ranks of cyclic covers of P1. This allows us to provably find all the rational points on the twist x sub 9. And so then we only have one x sub d left, namely x sub 1. So the d equals 1 case remains. And what we're going to do is we're going to take the genus 4 curve that was the first equation in x sub 1, and we're going to construct étale covers of that. So that curve is y1 cubed equals x times x cubed minus 6x squared plus 3x plus 1, and we can get étale covers of this form. Here, e is either 1 or 3 or 9. So if e equals 1, then the second equation gives us a rank 0 elliptic curve. If e equals 3, the second equation has no theoretic points, and so we only have to worry about e equals 9. But these e cases, remember, are really like a subcase of the d equals 1 case. So if e is equal to 9, that means that x cubed minus 6x squared plus 3x plus 1 is 3 times a cube. But because this is a subcase of the d equals 1 case, looking at the previous slide, x cubed plus 3x plus 6x plus 1 must be a cube. And that means that we get a rational point on this curve, y cubed equals this sextic. Why is that helpful? This curve y is a genus 4 curve whose automorphism group is isomorphic to S3. So it has lots of quotients. These are just the automorphisms defined over Q. I think that y actually has 18 automorphisms over larger fields. The quotient of this curve by a subgroup of order 3 is y squared equals x to the 6 minus 2x cubed minus 3. This is a genus 2 curve whose Jacobian has rank 0. So this curve z only has 3 rational points on it. And then we can pull these points on z back to y, points on y back to this étale cover, and then we've found all the rational points on the original genus 6 modular curve. Maybe now is a good time to pause and ask if there are questions about how this example worked.
There don't seem to be any
Okay.
questions.
So the next case I want to talk about the genus 43 curve. And let me talk about a little bit about where it comes from. So in 2006, Elkes posted a paper on arXiv about the modular curve parametrizing elliptic curves where the mod 3 representation is surjective and the mod 9 representation was not. So this modular curve that he wrote down was a degree 27 cover of the J line and is isomorphic to P1. So there are infinitely elliptic curves for which this happens. When we compute our list of subgroups, there's a maximal subgroup M of this subgroup H of index 27. So the modular curve x sub m will be a degree 729 cover of the J line. If we were to have an elliptic curve that corresponded to a rational point on this modular curve x sub m, then the mod 3 representation associated to this curve would be surjective, but the 27 torsion field of this elliptic curve would be the 3 torsion field adjoined zeta 27, which is basically as small as the 27 torsion field could possibly be, given the restrictions. This seems pretty unlikely. And this is maybe a suggestion that this modular curve x sub m might not have local points. So how can we test that? So what we do is we write down the canonical model of this genus 43 curve. Now the canonical model of a genus G curve lives in Pg-1. So this canonical model lives in P42. It's the vanishing set of 820 quadratic polynomials in 43 variables. This is not something you want to work with by hand. We want to show that this curve, we want to figure out if this curve has theoretic points or not. 3 is a natural prime to pick. If we take this model and reduce it mod 3, we actually get a scheme that has dimension 2, and this has 19 points in F3 on it. So we do the following thing. If for each of these points on XM mod 3, we lift the first 4 variables to some element of Z mod 9Z. Then we take that lift and we plug the values for the first 4 variables in to these 820 polynomials, and we create the ideal over Z generated by the values of these quadratic polynomials and 9. This is sort of a way of like doing Grobner basis computations over Z mod 9Z. So what we do is we check to see if 3 is contained in that ideal. If it is, then what that's saying is that there's no point, no mod 9 point on this modular curve whose first 4 coordinates are the lifts of the first 4 coordinates of the mod 3 point we started with. So we have to do a bunch of these computations. We have 19 points. For each of those 19 points, we have 81 lifts. So we have somewhere in the vicinity of maybe 1,500 points we have to test. In the end, we find that it's not possible to lift any of the mod 3 points of XM to mod 9 points. And that shows us that there are no mod 9 points on XM, which in particular implies that there are no rational points. I think now might be a good time to stop. I have some notes about what happens for the normalizer of the non-split Cartan mod 27, but I don't think I have quite enough time to get through them. And because we were not successful in finding all of the rational points on that curve, maybe I don't need to say too much about it. So I think I will skip ahead to my summary slide. So in summary, we almost classify the image of the theoretic Galois representation attached to non-CM elliptic curves over Q. We just don't know if there are any elliptic curves over Q where the mod 27 image is contained in the non-split normalizer of the non-split Cartan. We do this by writing down the possible theoretic images in GL2Z3. We compute equations for these modular curves x sub h, and then we find all of the rational points on these modular curves except for x non-split plus of 27. So thank you very much.